So it is a pleasure to have Daniele Alves talking about signals of the QCD Axion with a mass of 17 MeV today. So we have an hour, but if you do need some extra time, typically the seminars also last longer. So please take it away, Daniele.
Okay, great. Thanks. Thanks for inviting me to give a talk about this work. This work started about 3 years ago that we put out a paper with Neil Weiner. So I'll talk a little bit about that. And I'll also talk about my most recent paper that came out in the archive in September. So the motivation in particular for the most recent paper is some recent reported anomalies in the emission spectrum of E plus and minus pairs from transitions of excited states of the beryllium-8 nucleus and the helium-4 nucleus. I don't see, sorry, forgive me, I don't see my cursor. Do you see my cursor?
No.
No.
Well,
Okay,
you may
then.
have to change the keynote settings to make the pointer to appear.
Oh, do you know how to do that?
Yeah. In
we
this
see
way,
it now.
Yeah, in this way it would be visible when you are not in play mode.
Oh, so
Yeah.
do you mind if I don't use the play mode so I can point to places on the slide?
Oh, go ahead.
Okay, all right. Okay, so there were these anomalies that were reported in these magnetic transitions of the beryllium-8 and helium-4 nuclei. So for those of you who don't think about this every day, the definition of a magnetic transition is one that changes the parity and angular momentum of the nucleus by this relation here, shown at the bottom of the slide. Okay, so the data that is shown for both of these transitions in beryllium-8 and helium-4 is the invariant mass spectrum of this E plus and minus pair. And in both of these spectra, you can see that there is a visible bump here around a mass of 16 to 17 MeV. And so, I mean, in particle physics, if you have a bump on an invariant mass spectrum, that's a telltale sign of an on-shell resonance that is being produced and decaying to that particular final state. In this case, would be an E plus and minus pair. Okay, so I wish I could do a thought experiment of injecting these anomalies back in the 80s and seeing how people would respond. My bet would be that the first particle that would come to people's minds in trying to speculate whether this is a real anomaly that is some beyond the standard model effect would be the QCD axion. And that's because indeed this emission of the QCD axion in nuclear transitions was one of the first signatures that were predicted for the original QCD axion. And in fact, back in the 80s, there were some anomalies around. I think the one that generated most activity in phenomenology in trying to explain that as a emission of the QCD axion was called the GSI anomaly, which was a bump in the plus and minus invariant mass spectrum around 1.7 MeV. That unfortunately went away, but there is very interesting literature back then on trying to model build things to explain that anomaly. Okay, nowadays the QCD axion really is not the particle that comes to people's minds when thinking of these anomalies, and that's because the consensus that was built over the decades, especially because of constraints on the QCD axion, is that it should really be ultralight and cosmologically long-lived. And indeed, if that's the case, the axion would be a very attractive candidate for dark matter. So here I show, this is a plot that I borrowed from the PDG, and because of the very strong constraints on the axion parameter space from both astrophysical observations such as stellar cooling and also terrestrial constraints, pretty much all of the experimental focus on the QCD axion now is on this ultralight window where the axion decay constant is larger than 10 to the 8, 10 to the 9 GeV. Now, I suppose this audience is familiar with a significant challenge with this possibility, which is if you want to have the axion to be ultralight and cosmologically long-lived, then you have to implement the breaking of the PQ symmetry and therefore the PQ mechanism at scales that are very high, so greater than 10 to the 8, 10 to the 9 GeV. Which means that you're separating the solution to the strong CP problem from lambda QCD, which tells you where strong dynamics from QCD is taking place and where you have the strong CP problem by some 10 orders of magnitude. And then you run into the issue of worrying about whether this very delicate cancellation mechanism of the strong CP phase doesn't get ruined by spoiling effects that might come into place. And one of the effects that is the most discussed is non-perturbative gravity effects that might generate additional contributions that break the PQ symmetry and don't make it a good global symmetry to solve the strong CP problem. And so from this perspective of not wanting to have this very wide separation of scales between PQ scale and lambda QCD, it is worth considering implementations of the PQ mechanism closer to lambda QCD. But now the question is that experimentally viable? And so I'll try to answer this question in the context of these anomalies that were observed in these nuclear transitions. And so to explain this beryllium-8 and helium-4 axes via on-shell axion emission, the axion must have very, very specific properties that I will list now on this slide. The first obvious property is that the mass of the QCD axion should be where that invariant mass bump is, so around 17 MeV. And so from this very robust relation between axion mass and decay constant, that implies that the axion decay constant should be of order GeV, which means that the PQ breaking scale should also be order GeV. And that implies that there should be a new dynamical sector that is breaking the PQ symmetry at the GeV scale. So that's one of the implications. The other is that the axion must have suppressed isovector couplings to explain the spectrum of the two reported isospin transitions of beryllium-8. So there are two transitions that were investigated by this Hungarian collaboration that I just mentioned, of two excited states of beryllium-8 de-exciting to the ground state via emission of E plus C minus. So one of these transitions, which is some 17.6 MeV above the ground state, is mostly isovector. And you see here in the spectrum that there doesn't seem to be any apparent axis of the data relative to the expectation from internal pair conversion from this radiative decays. Now, the transition where you do see an axis is this other one, where the excited state is some 18 MeV above the ground state. This excitation is mostly isoscalar. That's where you see the bump. And so in order to explain these two spectra, one needs to have suppressed axion isovector couplings to explain why is it that the axion is not being emitted on this transition. And even in this transition here, even though it's mostly isoscalar, it does have a small isovector component. And that small isovector component could also be contributing to this bump, even at a rate that could be 1,000 times larger than what's observed if the axion has large isovector couplings. So all of this is to say that the axion isovector couplings, which are parametrized by the axion mixing with the neutral pion, should be smaller than its generic magnitude. So it should be smaller than about 10 to the minus 4. The generic magnitude of this mixing angle is 10 to the minus 2 for this range of decay constants. And so I call this axion piophobic because it doesn't like to mix with the neutral pion. And then, of course, to actually explain the size of this axis, one needs to have the right range of axion isoscalar couplings. And so parametrizing these couplings as mixings of the axion with the eta and the eta prime, these parameters should fall in this range of 10 to the minus 4 to 10 to the minus 3 to explain the size of this axis here in these beryllium-8 and helium-4 transitions. And the last property that the axion must have, obviously, is that it must decay promptly to an E plus C minus pair to be compatible with what was reported by this experimental collaboration. Okay, so this is a list of very specific properties of the axion. So this is a specific variant of the QCD axion. And what I find remarkable is that all of these properties that I listed that are motivated in explaining these anomalies are precisely the properties that make this the only variant of the QCD axion that is still possibly viable in this mass range of order 10 MeV. So now let me explain this statement now over the next few slides. I will go over all of the experimental constraints that have been accumulating over the decades on the QCD axion, and I'll show you why is it that this particular variant of the QCD axion, which is pyophobic, avoids these constraints. Okay, so the first property that I mentioned is a QCD axion with a mass of order 17 MeV, implying a breaking of the PQ symmetry around the GeV scale. So there is a generic implication to this statement, which is the following. If PQ symmetry is broken at the GeV scale, then the only fermions that you should really be charging under PQ symmetry are the light fermions. And that's because any fermion you charge under PQ symmetry should only have its mass generated after PQ symmetry is broken. And so the implication from this is that really only the light fermions should be charged under PQ. If you want to insist on charging, say, the bottom quark under this PQ symmetry, then you have to deal with very large Yukawa couplings, which are running into the non-perturbative regime, which then makes it very hard for you to find a perturbative UV completion for this model at the electroweak scale. So that's one argument as to why you don't want to charge, say, the bottom quark under U1PQ. But if you don't like these types of arguments, then I'll just say, well, this is forced upon you anyways by experimental constraints. So for example, if you charge the muon under PQ, then you have this coupling of the axion to muons, and this contribution of the axion to the muon magnetic dipole moment, G-2, is very large, way larger than what's observed. And so that would be excluded. And so if you want to avoid that exclusion, then you better not couple the axion to muons. And likewise, if you couple the axion to charm and bottom quarks, then you have very strong constraints from searches that have been done in radiative quarkonium decays to a photon and an axion. So this is J psi and upsilon. And the constraints that have been placed on searches for this also prevent any significant couplings of the axion to these quarks of the second and third generations. Okay, yes.
Can I ask you something? In other words, you have new matrices aside of the Yukawa matrices. You have new axion coupling matrices that are not commuting generally, right? Well, not necessarily with the Stern model Yukawa matrices, and therefore have some new sources of flavor breaking.
No, you see, Maxime, I've heard this argument before, and I'm frankly confused because I think this argument is precisely the opposite of what I'm saying. What I'm saying is that the axion couplings are exactly aligned with the mass basis. And so the axion coupling commutes with the it commutes with in the basis where you're in the mass basis for the light quarks, the Yukawa matrix.
Okay, so what happens when you include Stern model loops? The flavor changing neutral current loops like W top and is this commutation, is this carries through the loop processes or not?
So you would have to show me what loop you're talking about. I'd argue that sure, there is some degree of flavor violation in this model, but it's not coming from the alignment of the axion with the mass basis. Flavor violation here comes because you have to UV complete this model at the weak scale. Yeah. And so there at the weak scale, you have to introduce new Higgs doublets that are charged under PQ that couple exclusively to the first generation up and down. And so you can do this alignment in the mass basis by hand. Of course, you want to build a flavor theory that explains why this alignment is there, but there is nothing wrong with you just aligning it by hand, okay? So you don't have any flavor violation of the neutral components of this Higgs. The flavor violation comes from the charged Higgs. Now the charged Higgs will have off diagonal flavor components that will lead to transitions between, say, charm to up or strange to down, things like that. The charged Higgs is a problem. And then of course you have to play model building games, make the charged Higgs heavy, play with the parameters and do some song and dance, maybe add more stuff. But that's the usual problem that you have onto Higgs doublet models, that you have flavor violation from the charged Higgs. But the argument you're making, which I've heard before, which is you have flavor violation because you're aligning the quark in the mass spaces, that I don't see. It's precisely because you're aligning the quark in the mass spaces that you shouldn't have flavor violation, not at this level.
Well, once you include Stern model plus a loop process inside the Stern model, that's where it may, I don't know, I haven't looked in
Sure.
detail.
Yeah, Maxime, I think generically people expect a large flavor violation if you write down the EFT in the flavor basis. But however, Daniele here to begin with write down it in the mass basis. So,
That's fine. What I'm saying is that say take a top W loop, it induces Stern model penguin, but it may induce a penguin with axion in, you know,
sure.
photon.
But this doesn't
Because
induce
the axion is attached to an external leg. It's still valid thing, right? So I don't know if that's a problem or not.
Yeah, I think by counting it will induce the flavor violating effect smaller than the standard model itself. So in that sense, it's safe. And
Well, you might be right. I just don't see it, but
yeah, because you have to do one more close either one more loop or external insert one more extra.
What I'm trying to say, the 1 over FA is not a smallness at all, so it may be a problem.
Yeah, but I also think here Daniele will have ME over FA, when calculating many low energy observables, which is again further suppress the effect. But of course, from UV point of view, we may find writing down EFT in the mass basis a bit weird, but I think generically it's safe if you're okay with writing down this operator this way. So
can I say one more thing without actually thinking very carefully about this? If you're attaching the axion to external legs in this flavor processes, I'd say that's already accounted in the way I compute flavor violation in Kaon decays, for example, to axion by doing this in the low energy in the Chiral Lagrangian. I say that's already accounted in there. If you want to think of the axion being attached to internal lines, then sure, maybe it's not accounted there. But my point is the axion doesn't couple to tops. So
maybe not, right? So there's a question if there is a loop-induced d mu a times the axial vector current of S and D getting generated, right?
No, but that doesn't get generated in this. Yeah, that's the argument I've heard that I don't understand. You don't generate a coupling of the axion to a current that is SD, that is flavor violating or flavor transitioning. You don't do that precisely because I'm aligning the
even if I include the W interactions, which are which inside the loop, maybe the effect is small, but I will certainly generate such an amplitude.
Yeah, I think it will generate, but it's much smaller by loop order and by the ME over FA expression, I think.
Why is it ME? There is no ME here.
My point is okay. In this particular model, flavor violation comes from the weak interaction. Yes, the W will lead to transitions from S to B or Kaon decays, the usual thing. Okay, so yes, because the axion is coupling to quarks, then the axion will appear in flavor violating processes such as Kaon decays, K to pi A, for example. But that I am already taking into account when I consider the low energy effective theory of this, and I treat Kaon decays within Chiral perturbation theory. What you're pointing out of flavor violation of the weak interactions is taken into account in what I'm going to explain later.
Maybe, I'm not sure, but okay, go on. Yeah, we can get stuck at this point, yeah.
Okay, yeah, I'm happy to come back to it. Once I start discussing Kaon decays, if you want to bring this point again, I'm happy to continue to discuss it. Okay, one more comment I wanted to make, and I hope this is not going to generate confusion. Sometimes it does, which is, this is a model that has low PQ breaking scale. And so from a UV completion perspective, if you think about the couplings that you're generating between the axion and the standard model, a coupling that generically doesn't appear is axion to GG dual. So if you think about it, this coupling usually comes from integrating out heavy fermions that carry PQ charge. You integrate them out and then you generate this type of coupling. That's the case of KSVZ axion. But here, the axion couplings are appearing once you break PQ symmetry. And so the most natural place for the axion to appear is as a phase of the determinant of the light quark mass matrix. That's where the axion typically appears. If you,
but I think that this differentiation between the phase or this coupling, it's symbolic. It's not physical, because because in this way, if you effectively should have this GG dual coupling just to get a CP to restore CP, right? If it's not there, then there is no installation of the symmetry, right? So in this way, you can say that you can hide this coefficient into, I mean, phase of mathematics, but I think it is just pure theoretical division, not physical.
No, of course, you're absolutely right, because even if I write a model, I break PQ symmetry, and now the axion is appearing explicitly as a phase of the light quark masses, I can always perform a Chiral rotation and bring the axion in front of GG dual. But you see, once I go to the low energy and I'm working with degrees of freedom that are pions and kaons, and I want to work out those signatures, I don't want to have the axion here in front of GG dual, because I want to transition from my description of the theory in terms of quarks and gluons to a description of the theory in terms of mesons. And in order to do that and work in the framework of Chiral perturbation theory, I want to remove the axion from GG dual, bring it to the quark mass matrix, and then work from there.
Right, but in this way, then you do not need to say about lower scale or higher scale, because you always can do it.
Of course, yes, yes. So maybe in the next talk I give about this, I'll just remove this comment, because
because you see that it's no, it's a little bit symbolic, right? Because you all certainly can do it, right? So right. Okay, sorry.
No worries. Thanks for your input. Okay, all right. So the other requirement I mentioned, that the axion must have suppressed isovector couplings, right? So the way to parameterize the statement is to say that the axion mixing with the neutral pion should be less than 10 to the minus 4. This bound is coming from a search that was done back in the 80s by the Syndrome collaboration, where they looked for rare decays of the charged pion to electron, neutrino, and an additional E plus E minus pair. And they looked for resonances in the invariant mass of this additional E plus E minus pair. They didn't find anything. They only placed limits on this particular final state. So this branching ratio should be less than of order 10 to the minus 10. And that translates into this limit that I mentioned on the axion pion mixing. Now, what's interesting, I think, is that if the axion pion mixing is just a little smaller than 10 to the minus 4, then you can actually explain another anomaly. It's known as the K-TAV anomaly. So that is a discrepancy between the standard model expectation and the observed rate for neutral pion going to E plus E minus. This discrepancy is at the level of significance of 2 to 3 sigma. It's about 15% higher than the theoretical standard model expectation. And of course, you can make up for this discrepancy by saying that there is an extra contribution to this width coming from axion pion mixing. And the level of mixing that you need to explain this little axis is of a little less than 10 to the minus 4. I think that's interesting, that you could have something in the data that is indicating that there's something going on there on pion couplings to E plus E minus that could be showing some sign of the axion playing a role there. Now the question is this level of pyophobia even realistic in any model that you might try to build? So now let me try to go back to what I was mentioning and try to argue that this level of pyophobia is possible. So I mentioned we need a model that has PQ breaking scale at order GeV. So the most natural place for the axion to appear in this model is this here as a phase of the light quark masses. So these parameters QU, QD, and QS are just the charges, the PQ charges of these light quarks. Okay, so what does one do then? One then matches this Lagrangian just before QCD becomes strongly coupled to then the framework of chiral perturbation theory, where you're thinking of pions and kaons and the axion. And so if you just use chiral perturbation theory at leading order, you consider the axion a phase of the like quark mass matrix, and you just follow the standard procedure. You can compute what is the axion mass and what's the axion mixing with pions and etas and eta primes. And in particular, the expression that you get for axion pion mixing at leading order in chiral perturbation theory is given by this thing. So let me go discuss term by term here. Let me first talk about this term in the middle. This term in the middle depends on this parameter, which is the PQ charge of the strange quark. The natural size for this contribution to the axion pion mixing is at the level of 10 to the minus 2, if the PQ charge of the strange quark is order 1. And 10 to the minus 2 is way too large, right? I said we need this axion pion mixing angle to be less than 10 to the minus 4. So that means in order to be compatible with this requirement, the strange quark should have a PQ charge that is less than about 0.01. So, you know, the lazy way for me to deal with this is to say, well, I'm already not charging the other quarks of the second and third generation under PQ, so I might as well not charge the strange quark either. So I'll just by hand set the strange quark.
I'm sorry to interrupt, Daniele, but
yes.
Look, in this expression, if I look at this, if you would say that isospin 1 does not contribute, that both terms are disappearing, right? Because they are clearly isospin 1, right? So,
yes.
and it refers to both terms.
Yes, that's right. I'm just discussing term by term separately. So. First, I'm arguing, yeah. First, I'm arguing.
I mean, it is more generic argument, right? And remember, you already mentioned this about isospin.
Yes.
No, I mean,
yes. My point is, I want to claim that both of these terms are separately small. This term in the middle is small because by hand, I am turning it off by saying that the strange quark is not charged under PQ. And this is just a lazy way because I don't want to have to deal with model building something that has a large hierarchy in PQ charges, so I just set it to 0. It's not as ridiculous because I'm already setting the charm PQ charge to 0. So, okay, it's not, you know, an enormous stretch from what I'm already doing anyways. So I'm saying I don't have to worry about this because I don't have a PQ charge for the strange quark. Now I have to worry about this guy, yes? So the generic size of this contribution that comes from the PQ charge of the up and down quark is also at the level of 10 to the minus 2. So it's large for generic values of up and down PQ charges. But if you look at this expression here, you see that you get an accidental cancellation if you happen to have a model where the up quark PQ charge over the down quark PQ charge is 2. The reason why you get this accidental cancellation is that there is a near numerical coincidence in the ratio of down quark mass to up quark mass of about 1/2, right? So consider, for instance, using the most recent lattice determination of M up over M down of about, so the most recent determination is very close to 1/2. So if I plug this numerical value here in this expression, and I also, this is another long and boring expression that is suppressed by M up over M strange. If I also include this, then I get the prediction of chiral perturbation theory at leading order for axion pion mixing for this particular model that has this specific ratio of up over down PQ charges. This mixing is this, okay? So okay, if you look at the central value here, it's very small, but it's not significant because the error on this is enormous. But so my point is not to say that I have a very fine prediction for this mixing angle. My point here is to say that piophobia is compatible with the expectation that you have for this model for axion pion mixing. So the small value of 10 to the minus 4 is compatible with this range. Also, the values that you need for this mixing angle to explain the K-TAV anomaly in pi naught 3 plus or minus is also compatible with this range. So there is no incompatibility between observation and this particular model that naturally gives you piophobia because it's taking advantage of this near numerical coincidence of M up over M down being very, very close to 1/2.
What about the next to leading order effects in chiral perturbation theory? Could they have any effect here?
Yeah, they do. They are small. They're at the level of this. They're the same level of this error here. So 10 to the minus 3. So what they do is they just increase the error.
I see. Thank you very much.
Sure. Okay. So I hope you're happy with my argument that pyophobia is possible. It's not that ridiculous. So let me move on then to the final requirements that this axion must have, which is that it must decay promptly to E plus E minus. So this is actually the easy part. So it's easy to get the axion to decay promptly. That's just, you get that for free if you charge the electron under PQ symmetry with natural charges of order 1. So that's the coupling that you get for the axion with E plus E minus. And that gives very short lifetimes for the axion that are shown in this plot here. This is the parameter space of axion mass. And coupling of the axion to electrons as parametrized by this ratio of electron PQ symmetry over axion decay constant. And these dashed black lines show you contours of the axion lifetime. So you can get very short-lived axions that will not have problems, for example, with constraints from beam dumps that are shown here in, well, most of these gray regions are constraints from beam dumps. So this axion doesn't suffer from these constraints very terribly because it's very short-lived. There are also constraints from E plus E minus colliders that search for dark photons. Those constraints also apply here for the axion. That's, for example, constraints from Chloe and Babar that exclude these regions in green and in orange. You also have, there are more recent constraints from NA64 that explicitly looked for this hypothetical 17 MeV resonance that was reported by this Hungarian collaboration, and they placed constraints on this hypothetical resonance that in this parameter space translate into excluding this gray region here. But you see, at 17 MeV, you still have this, all of this parameter space indicated by this blue band that remains open. And it's compatible with PQ charges of the electron that are perfectly natural. They range here from 1/3 to about 2. And so there's no experiments that probe this axion coupling to electrons here precisely in this range that is favored by this variant of the QCD axion. Now, that is not to say that this is not going to be probed in the near future. Indeed, there's a very strong activity in the experimental community to search for visibly decaying dark photons in this mass range. And visibly decaying dark photons and axions are produced in the exact same processes. So for example, E plus E minus can annihilate to an axion and a photon, and there are searches that are looking for this. The axion can also be produced in fixed target experiments by impinging an electron beam on some fixed target of heavy elements. And then you can bram off an axion and look for an invariant mass bump in this E plus E minus final state. Also, the axion can give contributions to the anomalous magnetic dipole moment for the electron. And it turns out that the contributions of this specific axion to the electron G-2 happen to be within the range that you could even start to play games and try to explain this recent 2 sigma axis that has been reported for the electron G-2. So my point is, in the near future, if all of these experimental projections happen, they could probe very easily this parameter space, as it's illustrated here by these now colored lines that are experimental projections in this parameter space for upcoming experiments. I just have to make a disclaimer that this is a plot that I made back in 2017. So over the course of 3 years, this plot has been updated. Some of these sensitivities have been revised. Other experiments have been proposed, so this is not completely up to date, but it's just to illustrate that it's easy and to probe the axion coupling to electrons, and it doesn't suffer from all of the hadronic uncertainties of the axion hadronic couplings. And so this could be excluded shortly.
Hi, what's the preferred region for explaining electron EDM anomaly, as you mentioned?
Let me go to my backup slide. Yes,
oh,
it depends. So there are 2 contributions to the electron G-2 that are important here. There is the 1 loop contribution, which is just this. And then there's this bar Z type diagram at 2 loops. And so for this parameter space where this axion explains these anomalies, the contribution from these 2 processes are comparable, and you can make them constructively or destructively interfere. So if you don't want to make them destructively interfering, then you better have charges for the PQ charges for the electron to be smaller than 1/2. But if you want to push that to 1 or 2, then you just have to arrange for the sign of this PQ charge to be such that you have a small destructive interference between these two contributions, and then you can explore this whole parameter space and still be compatible with the electron G minus 2.
But these contributions are different order in alpha, right? So then you are saying the next order in alpha is cancel out, kind of previous order in alpha, which is then, okay, then you can wonder whether perturbation theory does work, because then why you would stop at next order? I mean, no, I understand that it's kind of, what I'm asking is kind of trivial, but still, you see this, if it's not special situation, it sounds a little bit out of normal order, right?
Yeah, it does. And I don't know if I go to the next 3-loop order, I confess I didn't see if I should worry about that. But you see, there is one thing that you should note. Here, this contribution depends only on the axion coupling to electrons, yes? Now here, this depends on the axion coupling to gamma-gamma, okay?
Yeah.
It just so happens that the size of the axion coupling to gamma-gamma is very different than the axion coupling to electrons.
No, I understand what you're saying, because, but then you should say that either first contribution is enhanced, or second contribution first contribution is suppressed, or second loop is enhanced, right? So
Yes.
so it is still kind of not some hierarchy then, which is hidden in this cancellation, right? So this is unavoidable, right?
This
Yes.
hierarchy, Arkady, is very common in say 2 Higgs doublet models, where you say calculate correction to the even in the standard model, right? If you take the Higgs contribution to the G minus 2 of the muon, regardless that it's small, right? The second diagram is giving more than the first diagram.
No. There I know there is, and I know logarithmic enhancement, and I know how it goes.
Yeah. Sure, but it's probably similar, right? Could be similar.
No. But then you need to see explicit parameter which explains this, right? I agree that it could be hierarchy.
Probably the coupling to quarks is a bit.
Yeah. So
the coupling to electrons, that's all.
Some explanations then of hierarchy. I mean, in the case you mentioned, you can understand what's going on, right? So,
of course.
Yeah, so it's okay. Yeah, but I'm sorry, may I return back a little bit and ask, when you consider a plus and minus annihilation in
Yes.
I wonder, in your previous slides, that I wonder that in certain way, specificity of this case is that here you can deal with particular CP eigenstates, right? So you can select the channel which is indeed CP breaking, right? Where normally, so Axion would be, you are checking CP of Axion, in this process explicitly in certain sense, right?
No, Arkady, there's gamma 5 enters in two vertices, right?
No, it's okay. No, I'm not saying that something is broken, but it means that you're producing a plus and minus in particular states, and in this way you are checking that you are producing this in the space state which correspond to like a negative CP or whatever, right? So it's nothing wrong with that. Of course, you can check this gamma 5 in any other process, but there in other processes there is no CP parity of initial states. What I'm saying. And here there is a CP parity of initial state.
Yeah, I don't know that, for example, so these searches, Chloe and Babar, were precisely looking for this process. Yeah. I don't know if they examined the final state spin and angular, the relative angle. I don't know if they did that analysis to try to target their exclusions specifically to vectors versus pseudoscalars.
Okay.
But they could, in principle, they could, especially if they see an axis, then they could start probing it.
You don't have any polarimetry of the final state electron spin, right? So it's not that easy. You can, of course, check for angular distributions and so on.
So you're saying Val doesn't have the ability to do that, Maxime?
Well,
I am not familiar.
If you have something like the tau decays, right, and then through tau decays, you can, through the distribution of parameters, you can reconstruct what the tau spin was, right? But for electrons, no, you cannot measure the electron spin in the final state.
No, but it's not spin. You are, I believe
angular distributions.
Angular distribution, right?
Yeah. They would be slightly different, yes.
Yeah.
Okay, all right, let me move on then now to the next property that the axion must have, which is its isoscalar couplings, as parametrized by its mixing with the eta and the eta prime, have to be in this range of 10 to the minus 4 to 10 to the minus 3 to explain the size of those beryllium and helium-4 axes. Okay, now this is the part that has the most confusion I found, especially in the literature back from the 80s. So let me tell you what people in the 80s did. They estimated this mixing angles at leading order in chiral perturbation theory, just like I exemplified a couple of slides ago when I showed you how to do the axion-pion mixing. And then based on the numerical values that they got from this leading order estimations, they computed the rate for charge kaon to charge pion plus axion. And based on this rate and experimental exclusions, they said, well, the incompatibility here then forces us to conclude that the axion with a mass greater than about a phi MeV is experimentally excluded. End of story. Let's just forget about it. Now, the argument that I made with Neil Weiner on our paper from 2017 is that you can't really rely on leading order chiral perturbation estimates of these mixing angles. They are not reliable. And that's because if you go to the next order in the chiral expansion, where you have operators at order p to the 4th, these operators can give order 1 contributions to these mixing angles. And now you have a problem because at this order, you have many operators, much more than at leading order. So this is just, I mean, this is more of like a dramatic effect, and there isn't any technical point here. But this is to show you have all of these many operators. Some of them have coefficients that are, the terminology of the field, they're called low energy constants or LECs. Some of these LECs are better determined, but other LECs are not well determined at all, or they are poorly determined. Nonetheless, they give large contributions to these mixing angles. And so what I'm trying to argue here is that if you take these uncertainties into account and you try to quantify them, and we try to do this a little bit, you conclude that at order p to the 4 in the chiral expansion, you introduce errors so large to the determination of these mixing angles, then that whatever argument was made of estimations of kaon decays and exclusions of the axion, they don't hold.
No, but look, Daniele, if you are taking this point of view, then you are saying that chiral perturbation theory is not applicable, and it certainly could be a case, but then just the whole approach of chiral perturbation theory doesn't make sense, right? Because it could be, because if you believe that it does make sense, then it should be hierarchy of contribution, lower order, higher order, right? It is basic of this chiral perturbation theory, right? So I certainly can imagine that chiral perturbation theory is broken. However, in the absence of real theoretical tools how to do it, people are using chiral perturbation theory. I mean, not because of love to it, but because there is not many variants how to do it, right?
Yes, I agree.
Yeah,
I agree, and I would say chiral perturbation theory is actually not great if you want to compute properties of the eta and the eta prime.
Yeah.
Then chiral perturbation theory is actually not very predictive. It's not predictive at all because you don't know the size of these coefficients.
No. I look. I remember, because I was, at my graduate time, I was very much involved in this soft pion, and these problems that you cannot describe, say, eta decays, eta prime decays. I mean, and when people are claiming that chiral perturbation theory describe it, I would not agree with it. So I'm I'm not saying that chiral perturbation theory works very well. I would probably say the opposite. But I'm trying to say that, in this way, then your reference to this higher orders is just to say that there is no range where chiral perturbation theory does work, right? Essentially.
Yes, exactly. Yes, if you try to estimate these angles in chiral perturbation theory, you run into the same problems that the eta and the eta prime have been describing chiral perturbation theory. And so my point is, forget about what chiral perturbation theory tells you about these angles. You don't have a way to calculate them. That's precisely my point. And that's precisely what I want to say on the next slide, which is...
Right. But people would say go to the lattice and calculate, right?
Go to the lattice. Yes, of course. But to the best of my knowledge, there has been no lattice attempt to determine all of the combination of the parameters that you would need to estimate this mixing angles. And so for lack of better information and better theoretical calculations for this, my point is the best way to approach this that we thought is to say we don't really have a reliable way to estimate this isoscalar mixing angles. And so the best way is to treat them as phenomenological parameters of this model. Sure, in the actual fundamental theory, they are not parameters that you're free to vary. They actually have specific values, but we don't know what they are. And so you treat them as parameters and you include them in the physical axial current. So this is the physical axial current, and I'm calling it physical because it's very important to say that this must be the physical axion, which is the mass eigenstate. This is the guy that you get after you take into account all of the mixings of the axion with the pion, eta, and eta prime. And so you can parametrize the physical axial current in this way. So you have here the axion mixing with the pion that appears in front of this current here, that is just the isoscalar current. And then you have the axion mixing with the eta and the eta prime that I chose to parametrize here in terms of the light quark isoscalar current, which is given by this, and then the strange current that is given by this. And of course, this is just a choice of parametrization. I can change to a basis where I have the octet current and the singlet current in chiral SU3. This is just a choice of basis, and I like the spaces better. I don't know, because I think that it's easier to make the plots in the spaces. But I hope this will not generate any confusion. And so my point is, I will treat these two mixing angles as parameters, and I will fit these anomalies that have been observed in terms of these mixing angles, and I'll tell you what the favored range for experimental data is for this mixing angles, and I will make no attempt to try to calculate them, precisely because I can't in chiral perturbation theory, and I am not a lattice gauge theory who will now go around and try to calculate these things from first principles. If this is clear, I'll move on.
Right, in this equality, I mean, technically, on the left, you have field A, on the right, everything should be then proportional to A, right? Which is not, I mean, I understand that you are talking about mixing, right? Yes. But I'm not sure about correctness of, I mean, putting that is identical in, because you should better say about matrix element or whatever, something, more or less directly related to measurable quantity, because here it's maybe statistical, but I'm not sure that the equation looks kind of consistent in a trivial sense, right?
Yeah. Okay. What I mean is this: there is that axion, which is this field that appears here, yes, as a phase of the quark mass matrices. This field here is not a mass eigenstate. It needs to be, so in order to go to the mass eigenstate, you need to diagonalize the mass matrix of the light pseudoscalars that include the pion and the scalars. And so my point is, the physical axion is a mixture of that field that appeared as a phase of the quark masses, of the neutral pion, And of these 2 degrees of freedom that I called eta UD and eta S, that will mix. So all of these guys here will mix amongst themselves to give you the physical eigenstate.
I'm sorry, I understand. So you're just rewriting physical axion in terms of those mesonic field. Okay.
Yes.
My question was incorrect. I'm sorry.
No, that's fine. But you see, I'm not doing this just to I don't know, to be fancy. The reason why I think it's important to define this current is sometimes people get confused. For example, if they want to compute the axion decay to gamma gamma, a common confusion is to take the PQ current, which is the current associated with this state here, look at the anomaly of the PQ current and say, oh, it's with this anomaly that I can compute the axion decay to gamma gamma. If you do this, you're doing it incorrectly. The right way to compute, for example, the axion rate to gamma gamma is to look at the electromagnetic anomaly of this current, which is the physical axion current. And this is important because the numerical answers you get, if you do it the wrong way or the right way, they're widely discrepant. And so you better know that you're doing the right thing. Yes?
No, I would say that when you're deriving anomaly, let's compare it with the derivation of anomaly of pi and normal pi 0 to gamma gamma, right? Yes. What we starting for? We are starting from axial current, like theoretical axial current, this is conserved, right? I mean,
yes.
Okay, if we would forget about electromagnetic interaction, okay, and then we are calculating. Let's say that it's conserved. Then what you're calculating matrix element of this current, right? And making this current conserved, right? Then you have this cancellation. I mean, due to conservation, and from there you're deriving that, say, for example, without anomaly would be 0, right? Decay would be right. Or when you have anomaly, you're finding a relation to anomaly. So it's indeed it's true that, how to say, you're not just substituting. But I'm not sure what you are saying in this way. It's equivalent to this. Maybe it is, yeah. But there is this kind of mixture there, because it's not that you're substituting pi and by, say, some particular state and calculating gamma gamma. Yeah, you're using so in this way, when you're saying that it is current, then you should say what is the anomaly of this current, right?
Yes, exactly. Yes, but my point is, if I want to compute the axion coupling to gamma gamma, I better be using this current and not the PQ current. Yes.
Yeah, I agree.
Yes. Okay, good. Okay. All right. So I also need to use this current and not the PQ current to understand the axion couplings to nucleons. Yes. So if I parameterize the axion generically in this way, where I have the isoscalar and the isovector couplings given by GA0 and GA1, then from that current that I just showed you, that trivially implies that the axion isovector couplings to nucleons is given by mixing of the axion with the pion times the axion pion to nucleons, then is then given by this. And the axion isoscalar coupling to nucleons is then given by the other quantities. And I hope these expressions are clear. I can belabor them a little more, or I can move on. Just explain notation. Delta U, delta D, and delta S are quantities that reflect matrix elements of quark axial currents within the nuclear state. In this particular linear combination, delta U minus delta D is the famous GA, that is 1.27. It controls neutron beta decay. These other linear combinations are not as precisely determined, but they're good lattice determinations of them as well. And you can just plug in their numerical values. Okay, but the point is now, if the axion couples isovectorally and isoscalarly to nucleons, then it can be emitted in nuclear transitions precisely because of this mixing with the pi naught, the eta and the eta prime. Yes. If these transitions have an energy split that is greater than the axion mass, of course, if you want to emit the axion on shell, And in particular, the rate will depend on what is the multipolarity of this transition. And by multipolarity, I mean the relation between total angular momentum and parity change of the transition. And so in particular, if this is a purely isofactor transition, the only parameter that contributes is the axion mixing with a neutral pion. So if it's a purely isoscalar transition, then the contribution comes from the axion mixings with these guys because of this particular coupling. I hope that's clear. Arkady, if you're saying something, perhaps you want to unmute yourself.
Yeah, I'm sorry. When you are saying delta U minus delta D, you know, I would say that it's just pi and n coupling constant, which you do know, right? I mean, normal one, right? So your delta U minus delta D in this sense is known, or I am not getting it wrong?
No, that's exactly what I said. I said this quantity here is very well known from neutron beta decay. Yes, it's 1.27,
I would say it's not from beta decay, just for pi and n coupling constant.
Yes, of course, that's right. You can always say it that way. Yes.
Or from the neutron lifetime is also known from there.
No, but pi and n coupling constant is directly related to what Daniele is saying, because
of course,
the transition this.
Okay, let's move on.
All right. Okay. So based on these axion couplings to nucleons, one can compute the matrix elements for these transitions. I did not compute this. People computed these in the 70s. So you have nuclear physicists and folks like Bill Bardeen, Jana Gida, Roberto Peche, Bill Donnelly. They computed all those matrix elements.
Daniele,
I didn't. Yes.
Daniele, this is a very sort of how to say, optimistic characterization of their work. It's not like really computed it, right? It's not on the standard of say some of your colleagues that are doing ab initio Monte Carlo, right, with this few nucleon systems. So it's not at the same level at all, right?
Yes, of course. When I say they computed, I mean they identified what are the parametric dependence of these transitions on these nuclear structure parameters, on nuclear matrix elements. That's what I'm saying. So, of course, they didn't actually compute those nuclear structure parameters, certainly not for beryllium-8. Back then, they weren't worried about this particular nucleus. So, of course, I have to introduce uncertainties in what these parameters are because I didn't compute them, they didn't compute them. And I have to introduce the uncertainties in the nuclear matrix elements. And I have to introduce uncertainties on the determination of the axion pion mixing. And so if I fold in all of these uncertainties, but I use this parametric dependence that they already understood in the 70s, then this is what I get. So this is the parameter space of the two axion isoscalar mixing angles. Yes, that I'm using on that basis of axion mixing with the strange current and the axion mixing with the light quark isoscalar current. Okay, I hope that is clear. So in the parameter space of these two isoscalar mixings, I can tell you what is the range in this parameter space that explains the beryllium-8 and helium-4 anomalies, taking into account all of these enormous uncertainties. And because the uncertainties are large, I get very broad bands. But if you lie inside these bands, which are the yellow and orange bands, and just to be clear, the yellow and orange bands, they overlap a lot. So the yellow band is not just this tiny sliver here, it's going under the orange band all the way up to here, right? So the yellow band goes from here to here. So these two bands overlap substantially. Yes, they're broad because there are uncertainties in this nuclear matrix elements and nuclear structure parameters that I haven't found anyone to compute them for me. But the fact that they overlap a lot indicates that the rate of these two axes that for axion emission from two very different nuclei is extremely compatible. Yes, you're not trying to stretch the theory or try to work very hard to make them compatible. They naturally want to be compatible and they want to live in this particular parameter space. And I think that's encouraging that they are, you don't, I mean, you get this for free, that they are compatible. And this also explains another thing that it's interesting. There were other transitions that were looked by this Hungarian collaboration and other collaborations. These were electric transitions. They have this relation between angular momentum and parity. And no axis were observed in electric transitions.
It's relation for angular momentum parity of what?
Of the change, so the nucleus makes a transition, so it changes its angular momentum and parity by this relation.
Yeah,
so
it is for the emitted particle in this sense.
Yes, that's right. Right. So the axion cannot be emitted in electric transitions because it's not compatible with the angular momentum and parity that you would need to carry away for these transitions. And so this is also a natural explanation as to why there is no observation of axion emission in any of the many electric transitions that have been observed. And this is not only in electric transitions of, so these reactions, let me make a small digression here. These excited nuclear states, they were produced via capture reactions of protons into a different nucleus. So you have this capture reaction and emission of, in this case, electromagnetic radiation, yes? That can either come in the form of a photon or an E plus, E minus. And this capture reaction can be resonant, which means you capture a proton and then the nucleus go into a resonant excited state, but they can also be non-resonant capture reactions. And the axion or a dark photon or a protophobic vector that are speculated as explanations of these axes, these particles, they should be emitted both in resonant capture reactions and in non-resonant capture reactions. The axion specifically will only be emitted in non-resonant capture reactions if these are magnetic transitions, electromagnetic transitions, yes? But most of these non-resonant capture reactions are not magnetic transitions, they are electric. And so that explains why you're not seeing the axion emitted there. Now, the folks who try to explain these axes with, say, protophobic dark vectors, they run into a problem there because their protophobic dark vector should also be emitted in these non-resonant capture reactions that are electric transitions. And there is no sign of observation there. And so this is a point that is not being made by me. This was recently made by some nuclear physicists at the University of Washington, Seattle. But my point is, whatever is their concern with those models that predict emission of particles in electric transitions do not apply here for the axion because the axion doesn't couple in electric transitions. Here's my rambling that I warned you about. I hope I didn't ramble too much to the point of being unintelligible. If anyone has a question and wants clarification, I can go on. Otherwise, I can switch subjects. Okay, so let me move on then. Okay, I still have, I guess, oh my. How much time do I have?
Well, typically we overrun the seminars anyway.
Okay.
It's the typical Minnesota spirit. So I would say just, we probably have another half an hour here. But
okay, all right. I'll try to not exhaust you. I'll try to finish in less than half an hour, but I still have two things I wanted to discuss, which one is now signals. So this were signals of the axion in nuclear transitions. Now I want to pivot to a different thing, which is the axion appearing in rare decays of charged and neutral kaons, okay? So this in principle is not very conceptually profound. I just argue that the axion mixes with the pion and the eta prime. And so you can use chiral perturbation theory and you can compute amplitudes for kaons to go to pions and eta primes off shell in the case of the eta prime. And then you have a way of computing all of those amplitudes and you can just stick in a mixing angle there. And then there you go, you get predictions for these kaons to pions and axions. This is how this calculation was done back in the 80s. And like I was trying to argue to Maxime, this is a perfectly legitimate way to describe this flavor changing dependence of the axion the way I decided to couple it. And it captures all of this flavor changing dependence. And there's no mystery there. That's just how it's done, because the flavor changing here is really due to the weak interactions and not because of the Axion direct flavor violating couplings to
My
quark.
question was if there are short distance contributions that would include Axion directly, but okay.
Yes. Exactly. Yes, and we have to draw. Yes, go ahead.
I don't want to stall at this point, but I'm not convinced. Okay, so
okay. Yes, but then at some point you could show me what short distance contribution you have precisely.
Yeah, of course, yes.
Okay, good. Okay, so so these are just yes, go ahead.
But you know, Maxim, if you are believing in this kind of chiral enhancement, right? Then it is what is written, right? Because what you are saying, it would be not enhanced, right? In terms of chiral limit, because here intermediate particle are light, right?
Yes. Is this a comment for me or for Maxime? I guess
it's for Maxime probably, because he suggested that no, it's true that it could be, you know, direct interaction of axion, not enhanced by, you know, this intermediate state, right? It's certainly true, but if you would think that those masses are normally so small, then it justifies.
The caveat here is that the axion coupling is 1 over GeV or MQ over GeV and not MQ over a weak scale. So I'm still, well, let's put it this way. I'll think it through, right? I'm not convinced that that's all.
Mm-hmm.
Okay, all right. But at least I hope that if I set that, at least these calculations for these contributions for Kaon decays are the way I show here. And okay, I think it's very tedious for me to go one by one, but I think you get the idea of how I translate these amplitudes weighted by mixing angles into decay rates. Now, there is one thing that I'd like to mention, which is the subtlety of octet enhancement in Kaon decays. So for those of you who haven't thought about this for a while, let me just remind you, forget about the axion, just in the standard model, you look at charge kaons and, for instance, K short, the CP even neutral kaon, and you look at their widths and they are different by 3 orders of magnitude. And that's very strange, right? You would naively expect that charge kaon, neutral kaon, they should have a similar hadronic width, and they don't. And chiral perturbation theory, again, does not explain that. You can certainly parametrize this large disparity because the operators that are contributing to charge Kaon decays, they at least a linear order in chiral perturbation theory, that's an operator that transforms as a 27-plet of SU3 chiral. And so you can say the coefficient in front of this operator is small. And then the operator contributing to K short decays to pi is an operator that transforms as an octet under SU3 chiral. And then you can say, oh, well, this coefficient happens to be large. And so you parametrize the disparity in widths as a disparity in the ratios or the size of these two coefficients. And in particular, to describe why you have this enhancement of K short hadronic decays relative to K charge Kaon hadronic decays, you need the ratio of these coefficients to be about a factor of 30. Okay, this is what is known as octet enhancement in Kaon decays. And of course, this is going to play a role here because in the same way that this amplitude is octet enhanced and this one is not, we'll have an issue here that some of these amplitudes will be octet enhanced and others will not. Okay, that's yes.
I'm sorry, but I mean, returning back to what Maxim asked, say why it could not be, say, a transition KL goes to KS and axion, and then KL decay, what K short would decay, but it would be not kind of due to you know, kind of this. No, it could be direct coupling, you know, of axion in KL KS transition, and it is good quantum numbers in terms of CP, right? Because it's CP breaking transition, right? KL KS. So in this sense, maybe for you, I don't know, when you're considering this you see that the difference would be that this transition KL, KS with axion would be not suppressed, right? In terms of CP breaking, it would be allowed transition.
Let me see if I understand. Are you asking me about this particular diagram?
Here you have epsilon k, right? Because it is CP breaking, right? And so, okay, but let's say that you are emitting instead of epsilon k, you are emitting axions there, and then it's not CP breaking, right? Then it's CP k.
Yes.
No, I mean just wonder if it would be kind of, maybe it becomes more visible in terms of experimental detection than this the emission of axion from KL KS transition.
Yeah, I have to say I got confused about your question. I'm not really sure. Are you saying that there's a contribution to K long decaying to pi axion that is not what I am showing in this diagram?
No, it's a different reaction. Imagine that instead of that you have the vertex KL goes to KS and emitting axion in this stuff. So there is a vertex KL KS axion, initial vertex. Okay. And then it would leave you to the KL goes to axion and say 2 pi, right, at the end of the day. So at the final state you have 1 axion and 2 pi, but this would be not this one should not be additionally suppressed as CP breaking, because CP is preserved in this decay. So and it's different final states than the one you are discussing. It's not the same, right? Because you have axion and 2 pi at there.
I guess I'm still confused. So I do account for K long decaying to 2 pions and the axion. Yeah. And it goes via this process. This is one type of decay. K long to pi and axion that is CP violating. Yes.
Right. So in this way you can look here, but I'm trying to kind of to relate it in a little bit different contribution, because you can say that it's the same final state. I agree, but imagine that this final state appears in such a way that axion is in the transition KL KS, and then KS goes to 2 pi. So it would be the same final states, but different contribution. No, I'm just referring to what Maxim suggested, where you have axion emitted at short distances, not due to mixing, right?
It's moreover, Arkady, what you're suggesting is the emission not due to the weak interactions.
Right. No, weak interaction would be in the decay of K.
In the K short vertex decay.
Right. But CP breaking is additional smallness, you see, because when you consider, you mean that epsilon K has a CP smallness. No, I mean.
Yes, but I better not have axion CP violating decays and not worry about whether I'm spoiling the solution.
No, it's not.
Daniele, what Arkady is saying, that take the mass term for the quarks, so like the d bar gamma 5d coupling to an axion, right? Because that's your starting point. Yes. Does this generate K long, K short axion vertex directly?
No.
Why not? It is CP preserving.
Yeah.
I'll tell you what
strangeness is preserved as well.
Yeah.
I shouldn't have the axion mixing. You're saying K long, K short axion. So you're saying that the axion could mix with K short, not because of its indirect mixing via epsilon K, but because of some extra axion CP violating contributions. And
why CP violating? Just a moment. Why CP violating?
Yeah,
because
about 3-point interactions between axion to K long and K short. It's 3-point interaction between axion and 2 mesons.
No, K long, I maybe do not follow. K long and K short has different CP, right? Opposite.
Yes.
But axion itself has opposite CP, so overall it's okay. So this vertex K long K short axion is CP conserving.
Yes, but are you saying that this is because of direct mixing of K short with the axion? Because I'm saying this should not be there.
No, it's not because of mixing. No, it's just that it is a transition.
No, Arkady, maybe she's right. So let's go from the K long, K short to K0 and K0 bar, right?
Okay.
So Axion cannot mediate delta S equals 2.
Okay, yeah, it could be the case.
Yeah, that's
it's probably because of,
Daniele, we retract.
because so I mean, I did not count this, but I agree that in this way, because of
it would have to be an axion insertion into a delta S equal 2 amplitude.
Right.
But at the risk of introducing even more confusion into the discussion, I'd like to say that there is a possibility of the axion mixing directly with K long.
Okay.
Because K long can mix with eta prime, and pion, and indeed it does. And then because of the mixing then with those light neutral scalars, you can have such a thing. And then you can have an axionic contribution to K long E plus E minus. And I'd say that in the future, this could be a very interesting signature for the axion as well. Okay.
But this, of course, it would be kind of at the level of weak interaction, right? I mean,
yes,
you can do it.
Yes. Okay, but I hope this discussion is about octet enhancement in Kaon decays that has nothing to do with CP violation. Yes, it's just the fact that K short is much broader than K plus, and chiral perturbation doesn't explain this. It just parametrizes by saying the coefficient of this octet operator is much larger than the coefficient of this 27-plet operator.
It used to be called delta I equal 1/2.
That's right. Yes, I think it's still called that. But because I'm including the eta and the eta prime, I like to think of these in SU3, in chiral SU3, yes, as opposed to chiral SU2. Okay, all right. Now, there is one more thing that I'd like to say, and I don't know how controversial this statement will be with you guys, but it's the following. From my perspective, the way that one implements octet enhancement in chiral perturbation theory is ambiguous. And some people dispute that statement. It's ambiguous because of this. In principle, there are two operators that you can enhance to parametrize octet enhancement in chiral perturbation theory. The first possibility is the standard implementation, which is via this operator that is shown here, that comes at first order in chiral perturbation theory, so order p squared. However, there is another operator that comes at the next order, order p to the fourth. It looks like this, and you could perfectly well just enhance the coefficient of this operator instead of this guy here. And you cannot, with existing data, distinguish these two possibilities because enhancement of either G8 or G8 prime provides an equally good phenomenological fit to all Kaon decay data, K to pi pi and K to pi pi pi, yes? And that's because of the degeneracy of the dependence of the amplitudes on these two coefficients. Of course, people, I think the standard view is that, okay, but why should I expect that there is enhancement coming of order p to the fourth if you just want naive power counting to hold, then the enhancement should come at p squared. But I think these are heuristic arguments. There is no way to prove that they are correct. And in fact, there has been some explanation of the possibility that octet enhancement comes from the enhancement of this operator instead of this one.
Yeah,
now,
but look, Daniele, it's similar to what we discussed before. Of course, you can say that a chiral perturbation theory does not make sense, right?
Yes.
It's very simple.
Yes,
it doesn't make sense. Of course, no, because I mean, the idea was that you can expand in momenta, and and this expansion could be applicable. No, of course, you can always say that it doesn't work. Hierarchy doesn't work, but it is equivalent of saying that do not use chiral expansion at all.
Yes, I'm almost saying that. What I'm saying is you can use chiral perturbation theory to compute this decay rates. That's what's normally done in the literature, especially in the 80s. That's what people do. And my point here is to point out loopholes and caveats. It's like, I mean, you can try to estimate rates in chiral perturbation theory, but you always have to be aware of the shortcomings of chiral perturbation theory and of the fact that your estimations might be different than what it actually is because of these issues. That's just to say, you cannot have confidence of these predictions of axion hadronic signatures because there is no reliable way to calculate that, unfortunately.
No,
Unless
no, but in terms of again, look, I'm thinking about like 1975, 76, when we did try to present some kind of explanation for delta equal 1/2 enhancement and try to explain all the processes, right? So there you can see kind of how this high orders in my it's a model, so it's not that, but it was the way to relate enhancement with these penguin operators. I mean, to have, okay, still there you can see this high orders in terms of expansion in momenta, that they're important, right? Even for high decay, right? But in particular model, you know how they look like kind of sigma meson additional whatever. So in this way, it's not just problem of chiral perturbation, it's a problem of understanding dynamics of the process, and it's indeed very much challenging. I mean,
yes, I agree with everything you said, and and this is precisely the argument as to why I say when you want to claim that this Axion model was excluded or not, you have to be aware of these caveats. So maybe if I go to my next plot, let me try to illustrate this. If I claim that octet enhancement or delta I equals 1/2 enhancement in Kaon decays occurs because of enhancement of this coefficient, then I can tell you that all of this parameter space in gray is excluded. And this is what the folks back in the 80s said. They said, oh, I calculated in leading order chiral perturbation theory that this angle should be, I don't know, around here. I'm just making up a place. It should be around here. But hey, this is excluded by Kaon decays, okay? And so this model is excluded, end of story. And I'm saying the story doesn't end there because one, whatever you estimate for this mixing angle using leading order chiral perturbation theory is not reliable. And on top of that, you're making the assumption that octet enhancement in Kaon decays is implemented via enhancement of this coefficient G8 of this operator here. And what I'm saying is, okay, all of these things are assumptions and they might not hold. And the reason why I'm saying this so forcefully is that if I alternatively implement octet enhancement in Kaon decays via enhancement of this operator G8 prime, then you can see how much parameter space opens up here that is not excluded by Kaon decays. Yes, let me show you again. This is the parameter space that is excluded if you have the standard implementation of octet enhancement. Now, this in gray is the parameter space that is excluded if you have the alternative implementation of octet enhancement. Yes, and so if you're fighting about whether somewhere here is excluded or not, then you have to be aware of these caveats. Whether you have a personal preference or other arguments as to why one already understands octet enhancement to be here and not there, and etc. That's another story. But I'm just saying the predictions are different depending on how you do this.
So let me just ask a question. In your first slide, so
this one,
when you question this extrapolation, which I guess this is what you're saying, is that you're extrapolating this octet enhancement to the axion decays.
Yes.
You don't necessarily need that to not hold for your explanation to work, or is that not true? So I mean, I still see some parameter space left here.
Oh yes, of course. Even if someone comes and proves that octet enhancement occurs via G8, you still have plenty of parameter space that is viable that could explain the helium-8 and beryllium-4 anomalies. So that's for sure, yes. Okay. But you see, it's not just that. Let's say I want to make predictions for an experimentalist to go and look for, say, K plus decays to mu nu axion, or K plus to pi a. You see, these predictions change depending on whether I assume octet enhancement via G8 or via G8 prime. I don't know if you can see that these lines are different. Look at the blue line here. This is the prediction for a branching ratio of 10 to the minus 8. Oh, I'm sorry. This is the one line that doesn't change. Look at the purple line.
Okay, I think I get it. But so these dashed lines.
Yes, these dashed lines, these are not experimental projections, just to be clear. These dashed lines are the points in parameter space where you get a benchmark prediction of 10 to the minus 8 for these particular channels.
I see. Okay.
And just not to make this plot awfully confusing, I chose 10 to the minus 8 for all of these modes, okay? Because if I choose different benchmarks for different modes, then I think that gets very confusing. Mm-hmm. That was the best way that I found to illustrate this in the form of a plot. But yeah.
Okay, thank you.
All right. Okay. Yeah, so that's my point. You have in either case, in either scenario, the two Kaon decay modes to axions that are extremely powerful in probing this parameter space are K plus to pi a. Oh, I didn't explain the difference between the left and the right plot. The difference is that I don't know what the relative sign between these two angles is. The relative sign could be negative or positive, and that's why I made two plots, okay? But the point is, K plus to pi a is very strong in probing this parameter space, and the other very strong decay is K long to pi a. That's also a channel where people should look for a signal of the Axon to potentially exclude that. All right, so let me try to talk about the final signature of the QCD Axion in rare eta and eta prime decays. I will go through this very quickly. This is just a trivial extension of what I discussed before. Just like the Axon can contribute to pi naught width to E plus E minus, it can also contribute to the width of eta and eta prime to E plus E minus. These channels have not been observed yet because they are tiny, tiny, tiny in the standard model. So there is a possibility for the Axion to give a non-trivial contribution to these channels that could be potentially observable in future eta and eta prime factories. And I can come back to these plots if you care about this. But let me go to the more interesting case, which is Axion decays to eta and eta prime. So this is very difficult to calculate. In fact, the person who brought these decays to my attention was Maxime, and he mentioned that if you do these estimations of eta and eta prime decays to pi a at leading order in chiral perturbation theory, you get an enormous rate that is excluded, end of story. But then to actually refine that calculation, it's complicated. One, because there are a variety of different methods that you can use to do that. And so the one that I thought was easier for me to do was to work in the framework of resonant chiral theory. This is a sort of UV completion of chi-pt, where you incorporate the low-lying QCD resonances. So you have the scalar, the vector, the exovector, and the pseudoscalar resonances that come above chi-pt. And you can incorporate these resonances and extend the principle of vector meson dominance to say that these resonances, they saturate the low energy constants of chiral perturbation theory, blah, blah, blah. Okay, so if you work on this framework, which seems to describe eta and eta prime decays quite reasonably, and then you extend it to include the Axion, you find that there are very important contributions from this resonant exchange, especially the scalar resonant exchange, the F0980 and the A0980, that also contribute with the same magnitude as the contribution from chiral perturbation theory at leading order. Yes, and the issue now is that you don't know what the size of these couplings are of the light mesons to these scalar resonances very well. You can try to use large NC limit arguments and also try to get some input from experiment to argue that the natural range for these couplings, which I parameterize in this funny way by making it dimensionless, the natural size for these couplings here, CD hat and CM hat, should be of order 1. And also data establishes that the relative sign between these two guys should be positive. So, but because we don't know that they're one, they're probably not, and we don't have a very precise way to determine that, I varied both of these parameters within plus or minus 20%, and then using these contributions to calculate the decay of eta and eta prime to pi a. This is the prediction for the branching ratios of eta to pi a as a function of these couplings in this framework of resonance chiral theory, in particular the couplings to F0 and A0. And again, this is the usual frustrating thing about this, which is the prediction varies by 2 orders of magnitude. It could be here in this range as large as a few percent and as small as 10 to the minus 4, okay? So my point here is, sure, I mean, Maxine is probably right that this is one channel that likely excludes this axion. But the point I make this is, well, sure, that's probably true, but you cannot argue that you know exactly what this branching ratio is, because there is a strong dependence of these branching ratios on these couplings. You are very close to a region where you have very large destructive interference, and maybe, just maybe, you're very lucky to fall around here where you might still have some hope of being compatible with observation. If anyone wants to comment or grill me on this, I'd be happy to respond.
Well, the reason we didn't write anything about it, we noticed this with Jun Wu and Robert, and because we knew that you know, next to leading order in Eta decays, they're as big as leading order and so on, and we were not sure which way it would go, constructively or destructively. So, and okay, so you're saying that there is a way of getting a destructive interference in this, and still be below or comparable to the Stern model, right?
Yes, there is a way. Yes, if you assume that this range of couplings is reasonable, and my point is it should be, because it's a 10% variation on these hadronic couplings, which is usually the error that you have on these things.
Yeah.
Okay, then let me finish. Oh, I'm sorry. One more thing. There is another problem here. Once you include these contributions from these resonance exchanges, then you can really modify the Dalitz phase space of these final states. And this is just an illustration. I choose 3 benchmarks for this theory here. In this benchmarks, I'm varying the masses and widths of these scalar resonances, the A0 and the F0. And then I show you what is the differential decay rate of eta to pi A as a function of the axion's momentum, right? And then if you have just boring flat phase space, you get this green curve. This is what you get, for example, in the standard model. But in this model, because you have non-trivial momentum dependence of these amplitudes, you can have very different Dalitz phase space. And this is important because it affects your experimental acceptance once you start putting cuts on these final state objects. That's just, okay. Another comment for someone who might be technically inclined into thinking about this.
So as one of the technically inclined people, yes, I can say that you don't have to produce Eta, right? So the Eta, some of the studies that are done by, for example, merging a proton with a deuterium, right? Yes. Producing an Eta or pi 0 and tagging on helium-3, right? Yes. So you can just take proton plus deuterium, produce your A and tag on recoiling helium-3. So that can be done at nuclear facilities.
Yes, that would be actually an excellent way to do it. Are you aware that someone have thought about doing it or have?
Well, I have people that, not specifically for that type of axion, but I have people at Kaon, at Ganil lab in France, in Normandy, okay, sort of interested doing the search of a boson, right? And so yes, they have very powerful beams up to like 30, 40 MeV, so fairly covering that mass range. But then they're fully sort of oriented on nuclear physics, not BSM searches. So it's a bit of a, you know, headwind if you want to do a BSM search at the nuclear facility. So we'll see how it goes.
Yeah, I hope you have better luck than I try to do something similar at Los Alamos. Los Alamos has a very nice neutron facility. And in principle, you could also produce the axion via neutron capture reactions, like you pointed out in your paper with David McKean.
Yes.
I thought that was a great idea. And I went and I talked to my colleagues and I said, can you do this? And they said, well, write a proposal, an internal proposal. I did. But you have a lot of politics also that, you know.
It's a polite way of saying go to hell, right?
Yes. Yes, I got a very strong go to hell from them because nuclear physicists, they don't like BSM stuff. They're extremely, extremely skeptical. Okay.
Well, what's not helping, of course, is this Hungarian group is a little bit being all over the map in the past, right, with their claims. So that doesn't really. I mean, like things will flip if any other nuclear, group with a lot of credo would suddenly see it, right? Then things would change overnight.
Yes, I totally agree with that. Yes, it's too bad that the Hungarians are, they could show a little less bias than they are showing right now. Okay, that was the end of my talk. This is my summary. I will continue to torture you with this. I'll just end here.
Okay, thank you, Daniele. I guess we can all applaud virtually. I'll stop recording just because we had enough